Hello friends, myself Dr. Girish Guru, Assistant Professor from Mahatma Phule Arts and Commerce College, Panvel. Today we will discuss the spacing between the parallel planes of a given Miller indices. On this article, questions will become question can be asked show that in a cubic crystal, so crystal system is specified over here, uh, show that in a cubic crystal system the spacing between the consecutive parallel planes of a Miller indices HKL is given by, and this equation is given. So we have to prove this equation. DHKL is equal to a upon underscore h square plus b square plus l square. Or the another kind of questions can be asked is find out the interplanar spacing for consecutive parallel planes of Miller indices. Or the another third kind of question that can be asked is find out the interplanar spacing between the HKL planes passing through the corners of the units. So here the planes passing through the system is given over here. Crystal system is specified over here. Just they have asked to find out the interplanar spacing for consecutive parallel planes with the Miller indices as is nothing but the HKL. So when we draw the crystallographic axes, we know everyone that we used to draw the origin generally, or to find the origin at one lattice point or atom, and then we extend the axes along the regular arrangement pattern. So this is x-axis, y-axis, and in the case of the HKL plane or the plane passing through the corner of the unit cell, then one plane will be at the origin and another plane is maybe at the given distances or given interceptor. So we have to find out the distance between these two parallel planes, so which is universally denoted by DHKL, because HKL is the indices which combined together represent the specific set of parallel planes. So we have to find out the DHKL interplanar spacing. So in order to do that, we have to consider the three coordinate axes as shown over here in this figure: OX, OY, and OZ in the coordinates Cartesian coordinate system. Then this is the HKL plane as shown by triangle. So this is the HKL plane, and this HKL plane intercept on the coordinate axes, like on x axis or x coordinate axis, it meets intercept at A. On y it is intercepting at B, and on z axis it is intercepting at C. So the distances along the intercept distances along the x, y, z axis is nothing but considered x, y, z. So as by the definition of Miller indices, we know the relation between intercept and unit translation vector and HKL. So which is nothing but the OA, that is the x, OA is equal to A upon H. Similarly OB is equal to P upon K, and similarly OC is equal to C upon L. In order to understand how this relation comes, we can consider one example where Miller indices has been firstly find out, and then this relation has been derived. Okay, so let us consider this HKL plane which meets the crystallographic axes at 3 points A, B, C, and where intercept in terms of unit translation vector is 3A along the x-axis, 4B along the y-axis, and 2C along the z-axis. So as per the steps of Miller indices, in order to find out Miller indices, first of all we have to take the reciprocal of the intercept. So it will be 1 upon 3 for x-axis, 1 upon 4 for y-axis, and 1 upon 2 for the z-axis. After this, what we used to do, we used to find out the LCM of this intercept, which is nothing but that 12. So in the next steps, we have to multiply this LCM to this intercept. So when we multiply this LCM, we will get the values 4, 3, 6, and we have to enclose into the circular bracket or parenthesis. So 4, 3, 6 combined together, you should represent this HKL plane, which is ABC. So now if by using the same relation OA is equal to A upon H, if we try to verify, I mean if OA is equal to A upon H, so H value is a 4, so it seems to be 0.25A, for B 0.33, 3b, and for OC it is nothing but 0.66667C. So these values will come, and if we see over here, the intercept OA is other than this 0.24a, means it is a 3a. But the one thing that we have to note down over here, we have multiplied by the LCM, and that LCM factor is a common in all these ratio. So if we avoid that common ratio, then still these ratios are means verified, so that this LCM is not considered over here. But in order to get the same values, what we can do, we can multiply this LCM, and we will get the same intercept values 3a, 4b, 2c along with three crystallographic axes OX, OY and OJ. So basically the LCM is not considered in this relation between the intercept, the new translation vector, and HKL. Okay, so you people has to note down this fact. Now let us consider the ON, which is perpendicular to the HKL plane and which is drawn from the origin. So when we draw the perpendicular on the this HKL plane ABC, this ON is to make the angle with the x-axis, y-axis, z-axis, which is nothing but the alpha, beta, gamma respectively. So ON is the distance which is nothing but the interplanar spacing between two successive planes, which is universally denoted by DHKL. So we are aiming to find out this distance, okay, in terms of ABs. So let us consider the triangle ONA, because in the figure you can see we have drawn the ON perpendicular on this triangle ABC. So what we have to do, we have to join this NA, and we have to consider the only triangle ONA. In this, the angle AON is nothing but the alpha, ONA is nothing but the 90 degree. Why? Because we have made perpendicular on this plane. So that, so in the right angle triangle, this which is nothing but the ONA, we can find out the relation of this alpha with the interplanar spacing and this ratio, or this x intercept, which is nothing but the A upon H. So cos alpha will be DHKL upon OA, which is nothing but the A upon H. So as H is at the denominator of denominator, so it will goes to the numerator, and so that cos alpha is equal to DHKL into H upon A. Similarly, the cos beta will be DHKL K upon B, and cos gamma is equal to DHKL L upon C. For the other right angle triangles ONB, ONC. Now we know the cosine square rule of directions, which is nothing but the cos square alpha plus cos square beta plus cos square gamma is equal to 1. So one can put this operator relation into this equation. So we will get this equation. So d is HKL into H upon A into bracket square plus DHKL K upon B into bracket square plus DHKL L upon C into bracket square is equal to 1. So over here DHKL is a common, so we can take out the common. So DH as it is a bracket square, so when we take out, it will be the D square HKL, so into H square upon A square or plus K square upon B square plus L square upon C square is equal to 1. So we can, as we want to find out the DHKL, so we can keep it to the left side, and this factor we can take out to the right side. So when it will take to the right side, it will go to the denominator. So we will get the relation, which is nothing but the D square HKL is equal to 1 upon H H upon A bracket square plus K upon B bracket square plus L upon C bracket square. So this relations we will get. So basically we can denote this relation DHKL is equal to 1 upon under square root H square upon A square plus K square upon B square plus L square upon C square. Now For cubic crystal system or cubic crystal structure, we know the unit translation vectors, that is RS equal, means the A equal to B equal to C. So we can put this relation over here. So instead of B and C, we can put A. So what will happen? The denominator will be same. So commonly it will be A square. So as it is a denominator or denominator, we can take it to the numerator, and as it is under the square root, so when we take out the from the square root, it will become A. So A upon under square root h square plus k square plus a square. This relation or the interplanar spacing we will get for the cubic crystal system, and it will be better if you try to find out the interplanar spacing DSK for different other crystal structure. Thank you very much for watching this video.